Deep underground, some believe that a sinister force is drawing near, and it's all connected to the European Organization for Nuclear Research, CERN, located on the border between Switzerland and France. Here, the Large Hadron Collider accelerates particles around its 16.8-mile track, smashing them together at near light speed. Many of the findings remain confidential within CERN. Why are the scientists so secretive about their discoveries? Let's explore the alarming discovery that some fear could instantly transport our planet to another galaxy. The Large Hadron Collider has several detectors, each with a unique purpose. ATLAS and CMS are designed to search for various particles, including the Higgs boson, which is believed to give mass to other particles. ALICE looks back in time to the Big Bang by studying quark-gluon plasma, a state of matter that existed just after the universe began. The Large Hadron Collider, despite its scientific aims, has sparked much debate. It requires a massive financial investment and complex technology. Each new discovery entails countless hours of setup, data verification, and analysis. This leads to questions about whether the scientific insights justify the enormous costs and effort. The Large Hadron Collider is a significant gamble, aiming to uncover new truths about our universe by smashing tiny particles together. When particles collide at high speeds in the Large Hadron Collider, they break apart, potentially revealing particles we don't usually see. The detectors around the collider capture this process, providing valuable data. This data helps physicists understand the forces that hold the universe together. It's like asking nature very detailed questions and interpreting the answers using the tools and language of physics. However, the Large Hadron Collider is just as much about generating new questions as it is about answering existing ones. Every discovery leads to more questions, keeping scientists busy with new theories and further experiments. The continuous process of questioning and testing is at the heart of science, yet it also signifies that there's always more to discover. Critics often ponder whether all this effort is justified. The expense of operating such a massive machine and the complexity of the experiments lead some to question if this is the most effective approach to understanding the laws of the universe. As conversations persist in academic and research circles, the significance and influence of the Large Hadron Collider remain subjects of ongoing discussion. This journey is essentially an ongoing cycle of exploration, discovery, and then striving to comprehend the new knowledge, which frequently adds complexity to our existing understanding. The process is demanding and intricate, requiring collaboration from scientists worldwide and significant resources. Whether the eventual results of the Large Hadron Collider will streamline our comprehension of the universe or introduce us to more intricate scientific puzzles remains uncertain. It's a dynamic journey where each experiment has the potential to unveil new paths of exploration, while also offering answers that could either support or question current theories. The finding of the Higgs boson, a crucial particle foreseen by the Standard Model of particle physics, marked a significant moment in scientific history. This model guides our understanding of how particles and forces interact, with the Higgs boson playing a vital role in explaining why objects possess mass. Picture a famous person entering a party and drawing attention, making it tougher for them to move around easily. Similarly, particles acquire mass by traversing through the Higgs field spread throughout the universe, and their interactions within this field grant them weight. The Higgs boson serves as a subtle indication of the existence of this field. When researchers at the Large Hadron Collider of the European Organization for Nuclear Research identified this particle, it wasn't merely a technical triumph or a theory match. It validated long-held forecasts. This revelation, often depicted as groundbreaking, essentially validated what numerous scientists had anticipated for a long time. While uncovering the Higgs boson was pivotal, it was less about unearthing something entirely novel and more about validating our current theories. This brings up a question about the typical path of scientific advancement. While it's thrilling to verify our predictions, does this method place too heavy an emphasis on confirming what we already understand, rather than delving into uncharted territories? The extensive endeavors to uncover the Higgs boson, which engaged thousands of scientists and substantial resources, showcase a dedication to validating established theories. Nevertheless, some may contend that such intense concentration on anticipated results could hinder the exploration of more speculative and potentially revolutionary concepts. Additionally, labeling the Higgs boson as the God particle is often done to inject excitement into the concept for the general public. While this can make the idea more captivating and relatable, it might also oversimplify or sensationalize the particle's significance in our comprehension of the universe. Science is a continuous journey of inquiry and revelation, where every solution leads to fresh inquiries. Taking a broader perspective, the validation of the Higgs boson represents progress rather than a final destination. It's significant because it bolsters the framework we rely on to interpret the physical realm. However, it should be viewed as a starting point for further exploration and inquiry, not the ultimate solution. The mysteries that remain are what make physics thrilling, areas where the standard model falls short of providing answers. These spaces are where we anticipate future scientific advancements to emerge. Let's now explore how the discovery of the Higgs boson reshapes our comprehension of the cosmos and the methods we employ in science. Looking at the significance of uncovering the Higgs boson, it's essential to ponder how we approach scientific endeavors. The emphasis on teamwork seen in projects like the Large Hadron Collider highlights the effectiveness of collective work in science. However, we should also consider whether our scientific practices, which tend to prioritize confirming existing theories, might sometimes neglect more speculative research that could yield innovative breakthroughs. Searching for the Higgs boson was akin to searching for a needle in a haystack, albeit on a massive scale. This elusive particle, while crucial, has a fleeting existence and can only be observed under extremely high energy conditions. Upon its creation, it promptly disintegrates into other particles. Detecting these particles and attributing them to the Higgs boson required not only a profound grasp of particle physics, but also remarkable precision in the technology employed. The task was immense. The detectors at the Large Hadron Collider had the monumental job of capturing and analyzing billions of particle collisions. Just envision the daunting challenge of sifting through such vast amounts of data to uncover even a glimpse of the Higgs boson. The energy levels required were so extraordinary that they stretched the capabilities of the Large Hadron Collider to their limits. Moreover, isolating the signal of the Higgs amidst the myriad of other particle interactions called for innovative approaches in data analysis and interpretation. Each potential sighting of the Higgs had to undergo thorough examination to ensure it wasn't a mistake or a case of misidentification. The importance of the Higgs boson discovery. So, why does the discovery of the Higgs boson matter? Well, it's a significant breakthrough because it confirmed a theory that scientists had been considering for nearly half a century and provided fresh insights into how the universe operates. The Higgs boson plays a pivotal role in the standard model of particle physics, which serves as our roadmap for understanding almost everything in the universe except for gravity. According to this model, the Higgs boson is linked to something called the Higgs field, which is an energy field present everywhere in space. As particles interact with this field, they acquire mass. Without the Higgs field, particles would zip around at the speed of light, making it impossible for the building blocks of matter celestial bodies like stars and planets, and even life itself to exist as we know it. Discovering the Higgs boson was a significant milestone in filling a crucial gap in the Standard Model, strengthening its foundation and validating the existence of the Higgs field as a tangible force shaping our universe. While the absence of the Higgs mechanism wouldn't cause an immediate collapse of the physical world, its confirmation has far-reaching implications. It not only verifies long-held theories, but also opens doors to new realms of physics exploration, potentially yielding breakthroughs as profound as those seen with quantum mechanics and relativity. Despite the substantial investment of public funds and effort into constructing these colossal detectors and conducting particle experiments, the immediate practical applications of high-level physics may not be readily apparent to most people. The benefits seem distant, relegated to theoretical debates rather than tangible everyday uses. Yet the pursuit of understanding persists, driven by our innate curiosity and the unyielding quest for knowledge. This venture is intricate and expensive, with outcomes that may initially seem intangible. However, it propels forward, fueled by our curiosity about the universe, its mechanisms, and our place within it. Each revelation, regardless of its abstract nature, contributes a piece to the grand puzzle of our cosmos, gradually painting a clearer picture of the reality we inhabit. The Higgs boson turned out to be lighter than expected, which is surprising given its interactions with other particles. This unexpected lightness suggests there are aspects of physics we haven't yet uncovered. This discovery is pushing scientists to delve into even deeper questions, such as the nature of dark matter and the possibility of other dimensions we are unaware of. Dark matter comprises about 27% of the universe. It doesn't emit, absorb, or reflect light, so we can't observe it directly. We know it exists because of its gravitational effects on galaxies and galaxy clusters. Researchers believe that studying the Higgs boson could lead to the discovery of new particles, offering insights into dark matter and possibly revealing astonishing facts about the universe. These might include the existence of parallel universes and intriguing phenomena like the Mandela effect. The discovery of the Higgs boson is crucial for understanding the early universe, right after the Big Bang. During this period, the universe expanded rapidly in an event known as inflation, and the Higgs field might have played a role in this process. By studying the Higgs boson in experiments at the Large Hadron Collider, scientists can gain insights into the conditions of the universe shortly after it began, helping us understand how it has evolved over time. Next, let's explore how the Large Hadron Collider aids us in uncovering the fundamental building blocks of the universe. The explorations at the edge of space and time. The Large Hadron Collider acts like a time machine, allowing scientists to recreate the conditions of the early universe just moments after the Big Bang. By doing this, they hope to understand how the universe's fundamental building blocks came together. One of the most intriguing concepts in physics is the multiverse theory, which proposes that our universe might be just one of many, each with its own set of physical laws. This idea arises from combining quantum mechanics with theories about the universe's rapid expansion right after the Big Bang. According to this model, different regions of space might have ceased expanding at different times, resulting in multiple separate bubble universes. The Large Hadron Collider could help us determine if the multiverse theory is true. It conducts experiments to find signs of extra dimensions and unusual particles. If gravity can travel between our universe and others through these extra dimensions, we might detect it at the Large Hadron Collider. Additionally, discovering tiny black holes at the collider would be significant because it would suggest the existence of more dimensions than we typically observe. Studying the Higgs boson at the collider might also provide insights into these possible other universes. If the properties of the Higgs boson, such as its mass, appear finely tuned to support life only in our universe, it could indicate that other universes have different physical laws where life as we know it wouldn't exist. The Mandela effect is another fascinating topic. It occurs when many people remember an event differently from how it actually happened. Some believe this could be evidence of parallel universes influencing our own. While the Large Hadron Collider primarily focuses on particle physics, its research into dimensions and fundamental forces might indirectly help us understand whether parallel universes exist. The Large Hadron Collider is also vital in the search for dark matter. Dark matter doesn't interact with light or electromagnetic forces, making it invisible and intangible in the traditional sense. However, it is crucial for explaining the rotation of galaxies and the movements of galaxies in clusters. The Large Hadron Collider aims to detect dark matter by searching for signs of it in high-energy particle collisions. Although dark matter particles would pass through detectors without being noticed, scientists can look for missing energy and momentum in the collision data, which might indicate the presence of dark matter. This search is akin to looking for an object's shadow rather than the object itself. Just as a shadow can reveal the shape and size of the object casting it, the missing data in particle collisions can provide clues about the properties of dark matter. As we continue to explore these concepts, they constantly push the boundaries of our knowledge and challenge our traditional views of reality. Exploring the concept of dark matter, various theories propose potential particles that the Large Hadron Collider, LHC, might detect. Among these theories are weakly interacting massive particles, WIMPs, which could interact with regular matter or transform into detectable particles. The LHC isn't just smashing particles together for fun, it's meticulously searching for any signs of dark matter, which might reveal itself by influencing the behavior of the Higgs boson, a particle thought to interact with all massive entities. If dark matter has mass, it's likely to interact with the Higgs field. Understanding this interaction could provide insights into whether the Higgs mechanism could help us learn more about dark matter. As the LHC's experiments become more sensitive and data analysis more precise, the chances of detecting subtle hints of dark matter increase. Some might argue that this pursuit of dark matter is as much about testing our scientific tools and theories as it is about discovering new aspects of the universe. With each experiment and analysis, researchers make small advances. But what are we truly gaining from this? By pushing the boundaries of our knowledge and challenging our traditional views of reality, we not only get closer to understanding dark matter, but also enhance our scientific methodologies and tools. This pursuit deepens our comprehension of the universe and enriches our grasp of fundamental physics, leading to potential breakthroughs that could transform our world. With this in mind, the European Organization for Nuclear Research has upgraded the Large Hadron Collider to create the high-luminosity Large Hadron Collider. This is not just a minor improvement, it's a significant enhancement of the machine's capabilities. High luminosity means increasing the number of particle collisions. By doing so, the High Luminosity Large Hadron Collider will gather data faster, capturing rare events that were previously too infrequent to observe. This increase in data is expected to provide better quality observations, potentially uncovering new phenomena or offering solid evidence to support or challenge current theories. The High Luminosity Large Hadron Collider has ambitious goals. It aims to delve deeper into theoretical realms, searching for evidence of dark matter, exploring the possibility of extra dimensions, and investigating other phenomena that might explain the fundamental elements of the universe. The High Luminosity Large Hadron Collider also aims to measure the properties of the Higgs boson more accurately. These measurements are crucial for exploring the limits of the Standard Model and potentially discovering new physics. Achieving these goals involves more than just increasing particle collisions. It requires significant advancements in the technology used to detect and process data. Upgrades are being made to the ATLAS and CMS detectors, which are essential for the collider's experiments. These improvements include new sensors and electronics that can handle higher radiation levels and record data faster than before. For instance, new tracking detectors being installed at both ATLAS and CMS are vital for tracing the paths of charged particles after collisions. These upgraded systems are more intricate, enabling better distinction between significant events and background noise. Nevertheless, one might ponder whether, amidst all these enhancements and the constant influx of data, we are genuinely edging closer to comprehending the universe, or if we're merely chasing theoretical possibilities, hoping they materialize into something substantial. As the Large Hadron Collider progresses, it becomes challenging to discern if we're uncovering fresh truths about the universe or simply reaffirming existing beliefs. However, with the latest upgrades, the High Luminosity Large Hadron Collider brings us even nearer to grasping the complexities of fundamental physics. The high stakes of high luminosity. Advancing our understanding of the universe through the Large Hadron Collider is a gradual process made up of countless small steps forward. Each piece of data, each experiment, contributes a tiny fragment to the immense puzzle of the cosmos. The hope is that, over time, these fragments will come together to paint a clearer picture of the universe. However, the intricacy and nuance of the data mean that each discovery raises new questions. It's an ongoing cycle of hypothesis, experiment, and refinement. With the enhanced capabilities of the High Luminosity Large Hadron Collider, we can now explore realms of particle physics that were previously beyond our reach. This could result in breakthroughs in our understanding or affirm that our current theories are on the right path. The journey of discovery is slow and fraught with technical hurdles, demanding not only new machinery but also fresh perspectives on the data we gather. As the High Luminosity Large Hadron Collider sets the stage for future breakthroughs, the scientific community eagerly anticipates its discoveries and reflects on their implications for our understanding of the universe. With the collider preparing for its next series of experiments, it's evident that both significant opportunities and challenges lie ahead. The latest upgrades aim to enhance particle tracking, enabling scientists to better examine the aftermath of particle collisions. This is essential for deciphering complex subatomic events, akin to understanding a movie by watching more than just the final scene. While hardware enhancements are crucial, managing the anticipated influx of data presents a significant challenge. Current computer systems are already stretched, and with the projected increase in data from the High Luminosity Large Hadron Collider, there's a pressing need for a robust plan to handle this influx. Artificial intelligence and machine learning are stepping up to address this challenge. These technologies are being refined to sift through vast datasets, identifying crucial patterns and anomalous results that could indicate new scientific breakthroughs. The capability of these systems to efficiently and accurately manage, analyze, and interpret large data sets is not just advantageous, it's essential for the collider's success. Quantum computing holds the promise of processing data at speeds currently beyond the capabilities of traditional computers, potentially addressing the escalating computational demands. However, the practical application of quantum computing in data analysis remains more of a vision than a reality, with tangible uses still distant on the horizon. With each experiment and every piece of data scrutinized, we edge closer to unraveling the deeper truths of our universe. Yet, this scientific pursuit is not solely about uncovering new discoveries. It also raises a host of ethical concerns and public anxieties. The powerful collisions occurring within the Large Hadron Collider not only spark scientific curiosity, but also prompt serious safety considerations. The concept of generating micro-black holes, although refuted by scientists, has captured public imagination and evoked fears. Despite theoretical assurances that these black holes would swiftly dissipate through Hawking radiation, the notion of intentionally creating them on Earth can be disconcerting. The European Organization for Nuclear Research has responded to concerns by conducting extensive safety studies and collaborating with top physicists to address any potential risks. These studies confirm that micro-black holes, even if formed, would dissipate too quickly to pose any danger. Despite these assurances, public anxiety persists, prompting questions about whether these explanations suffice or are merely attempts to calm fears rather than provide thorough understanding. The journey of discovery at the high-luminosity Large Hadron Collider is marked by scientific excitement alongside a web of practical and ethical challenges. As we delve deeper into the mysteries of the cosmos, we must navigate the complexities of managing vast amounts of data, addressing public apprehensions, and upholding ethical research standards. Each advancement is closely monitored by an attentive public, adding layers of responsibility to the scientific community's pursuit of knowledge. As the Large Hadron Collider pushes the limits of our understanding of the universe, it also tests our capacity to handle data and public perception. Balancing these elements is integral to the scientific process, as crucial as the experiments themselves. Maintaining trust and understanding between the European Organization for Nuclear Research and the broader community is crucial as we delve into the fundamental forces that govern our universe. The organization emphasizes openness and transparency in its high-energy particle physics experiments, supported by various public outreach and educational initiatives aimed at explaining its work and potential impacts. It also asserts adherence to rigorous international safety standards, overseen by scientists and safety experts worldwide. However, there are valid questions about the sincerity of these efforts. Some may view the information shared through these programs as more of a public relations strategy, focused on alleviating public concerns rather than fostering genuine comprehension. The details provided often accentuate the positives while downplaying potential negatives. While strict safety protocols and continuous monitoring are reassuring, they may also be perceived as attempts to downplay concerns about the risks associated with these experiments. These risks are genuine and could result in unforeseen consequences despite the precautions taken. There are ethical considerations that often go overlooked. For example, operating a facility as massive as this one has a considerable environmental impact due to its high energy consumption. Additionally, there's a debate about the value of the funding allocated to particle physics research. Some argue that these resources could be more effectively used to address pressing issues like poverty or healthcare. Let's examine the practical implications and hurdles associated with conducting advanced physics research. The price of pushing dangerous boundaries. Furthermore, there's an important question about the practicality of the knowledge gained from these experiments. While unraveling the mysteries of the universe is undoubtedly impressive, it's worth pondering whether these scientific advancements will directly contribute to solving the urgent challenges faced by people today. This dilemma puts the European Organization for Nuclear Research in a difficult position, torn between its pursuit of expanding human knowledge and the need to justify these costly projects in a world with numerous pressing needs. Moreover, the ethics of prioritizing research with potentially distant practical outcomes spark debate. At a time when many worldwide struggle with basic necessities, allocating significant resources to theoretical endeavors can appear disconnected from global priorities. This underscores a fundamental conflict, balancing the advancement of scientific understanding with addressing immediate human conditions. These considerations suggest that while the work of the European Organization for Nuclear Research is groundbreaking, it raises questions about its true impact and value. The ongoing debate about whether potential scientific breakthroughs outweigh the considerable expenditure and environmental costs reflects broader societal discussions about the role and responsibilities of science in tackling real-world problems. The prioritization of scientific projects frequently ignites passionate debates within and beyond the scientific realm. To mitigate these discussions, the European Organization for Nuclear Research endeavors to validate its experiments scientifically while upholding ethical and environmental standards. The organization conducts thorough environmental impact assessments and seeks opportunities to reduce energy consumption and waste. However, one might question the efficacy of these efforts, pondering whether they genuinely address environmental concerns or merely serve as superficial gestures to placate critics. Thanks for watching. If you enjoyed this video, don't forget to like, share, and subscribe for more content. Stay tuned for our next video, where we'll explore even more fascinating topics. And remember, keep questioning, keep exploring, and keep learning. See you next time.